In this video, we will consider trigonometric identities. The material corresponds to section 7.4 of the textbook. We'll begin with some definitions. Let's say we have two functions, f of x and g of x, and we know that for any given value of x, these functions are equal. If that's the case, then we can say that the functions are identically equal. The equation f of x equals g of x is called an identity. Here's an example. The equation x plus 1 squared equals x squared plus 2x plus 1 is true for any value of x. This equation is an identity. We can always substitute the expression on the left side of the equation for the one on the right side, and vice versa. Any equation that's not an identity is called a conditional equation. Here's an example of one. X squared equals 4. This equation is true for only certain values of x, namely -2 and 2. Trigonometric identities are really useful for simplifying expressions and equations involving trig functions. There are some really common ones that we've already seen in our studies of trig functions. Now we'll look at them systematically. These trig identities can be grouped together by type. The first type are called quotient identities. They are very convenient ways to relate both tangent of theta and cotangent of theta to the more basic trig functions sine theta and cosine theta. The second type are the reciprocal identities, which are useful for relating all 6 trig functions to each other. Every trig function has a reciprocal function. The third type are the even-odd identities. Sine theta, along with its reciprocal function cosecant theta, as well as the reciprocal pair tangent of theta and cotangent of theta, are all odd functions. Their graphs are symmetric about the origin. The cosine function, along with its reciprocal function, the secant function, are even functions. Their graphs are symmetric about the vertical axis. The fourth type of trig identity is called the Pythagorean identity. It's called this because the foundational Pythagorean identity, shown here in blue, can be thought of as the application of the Pythagorean theorem to a first quadrant angle. The equation describes a right triangle in that quadrant, whose hypotenuse is 1 unit long, and which has sides of length sine theta and cosine theta. The other two Pythagorean identities can be obtained from the first one by dividing every term by either cosine theta or sine theta. You should memorize all of the quotient, reciprocal, and even-odd identities. You should also memorize the first Pythagorean identity and be able to derive the other two from it. Memorizing all these identities is not very difficult if they're used frequently, solving problems like the following examples. Sometimes we're given complex trigonometric expressions that we want to simplify. One technique is to rewrite the expression in terms of sines and cosines only. Let's try that on the expression shown. We replace cotangent of theta with cosine theta over sine theta in the numerator and cosecant theta by 1 over sine theta in the denominator. This is a complex fraction. When we divide something by a fraction, it's equivalent to multiplying it by the reciprocal of that fraction. So this expression equals cosine theta over sine theta times sine theta over 1. And that equals cosine theta. Now let's consider an identity that we haven't seen before, namely cosine of theta over 1 plus sine theta equals 1 minus sine theta over cosine theta. We want to prove that this identity is true. To do so, we need to rewrite the equation so that the expressions on both sides are the same. One approach is to take the more complicated side of the equation first and simplify it. and then do the same to the less complicated side until they match. Here, the two sides are of about the same complexity. We could argue that the left-hand side is a little more complicated because the denominator is a sum rather than a single expression. So let's begin by trying to simplify the left-hand side. The complicated thing about the left-hand side is the denominator, as we've already noted. We can simplify it by multiplying by what's known as a well-chosen one, namely a specific fraction that has the same numerator and denominator, which means that it equals 1. It's called well-chosen because it does a specific job, that is simplification, in changing the way an expression is written. Here we are multiplying the left side of the equation we've started with by the fraction 1 minus sine theta over 1 minus sine theta, which equals 1. When we do this, we obtain the product cosine theta times 1 minus sine theta in the numerator and 1 minus sine squared theta in the denominator. So the denominator actually looks more complicated than it was before. So why would we want to do something like that? The reason we do is because according to the basic Pythagorean identity, the denominator actually equals cosine squared theta. So we replace it with that, and then we see that cosine theta is a common factor to the numerator and the denominator, so we can divide both the numerator and the denominator by the cosine of theta. And when we do, we end up with 1 minus sine theta over cosine theta, which matches the right-hand side of the original expression. So now let's look at another example. Here's one where the goal is just to simplify the expression. Notice that there's no equal sign. This is just a pair of fractions. We know that the usual thing is to rewrite the fractions so that they have a common denominator, which will allow us to add them. The common denominator here is sine u times cosine u. So we multiply the first fraction by cosine u over cosine u, and the second fraction by sine u over sine u, and both of these multiplications are by well-chosen ones. This allows us to add the two fractions, and we get the expression shown when we do. The numerator has 4 terms, but 2 of them are actually inverses of each other, and they add to 0. So we can actually cross them out. Every term in the expression is a sine or cosine except for the cotangent term. We can replace it with its quotient identity to help simplify the expression. And here's what we get when we do. And we can cancel out the sine u terms in the numerator, leaving cosine u plus cosine u in the numerator. And the numerator further simplifies to 2 cosine u. The expression equals 2 over sine of u, and that's as simple as we can make it. Now let's simplify an expression using factoring. We begin with sine squared of v minus 1 over tangent of v times sine of v minus tangent of v. So what can we do with this? The numerator can be considered the difference of 2 squares, which we can factor into sine of v plus 1 times sine of v minus 1. In the denominator, tangent of v is a common factor, so we'll factor it out. When we do, we see that sine of v minus 1 is a common factor to both the numerator and the denominator. We cancel out the common factor, and we're left with sine v plus 1 over tangent of v. And that is as simple as we want to make this. Now let's say that we want to show that cosecant of theta times tangent of theta equals the secant of theta. We see that the left side of the equation is more complicated than the right side, so let's work in simplifying it. The simplifying approach we'll take this time will be to convert both terms into expressions only made up of sines and cosines. Cosecant of theta equals 1 over sine theta, and tangent of theta is sine of theta over cosine of theta. The sine terms cancel, leaving 1 over cosine of theta, which equals secant of theta. So we've proven that the equation is an identity. Here's another identity we would like to establish. We begin with the equation sine squared of minus theta plus cosine squared of minus theta is equal to 1. We rewrite the equation so that it's clear that the trig functions are both squared. And then we use the fact that sine is an odd function, meaning that the sine of minus theta equals minus the sine of theta, and that the cosine is an even function, meaning that the cosine of minus theta is equal to the cosine of theta, to again rewrite the equation. Squaring minus sine of theta equals sine squared of theta. And now we have a result that matches the first Pythagorean identity. The next example is more complicated. We would like to establish the identity shown. The best way to do so is to simplify the left-hand side until it matches the right-hand side. Just like we did in the last example, we rewrite the squared trig terms so that it's more clear that they are squared. We replace sine of minus theta with minus sine of theta, and cosine of minus theta with cosine of theta in both the numerator and the denominator, taking advantage of the fact that we know that the sine of an angle is an odd function and the cosine of an angle is an even function. When we square minus sine of theta, we get sine squared of theta. We can factor the numerator, which is the difference of two squares, into the terms sine of theta minus cosine of theta times sine of theta plus cosine of theta. We can factor a minus 1 out of the denominator too. When we do this, we can see that sine of theta plus cosine of theta is a common factor between the numerator and the denominator, so we can cancel it out. That leaves us with sine of theta minus cosine theta, all divided by 1. And that's equal to cosine of theta minus sine of theta, so we've shown that the equation is an identity. Here's another identity that we'd like to establish. Given that the left side of the equation is more complicated than the right, we will simplify the left side. Given that the right side is the tangent function, we will try to express the left side in terms of tangent functions as much as possible. We start by changing the cotangent of u into 1 over the tangent of u. Next, we combine the terms in the denominator into a single fraction. We recall that dividing something by a fraction is equivalent to multiplying it by the reciprocal of that fraction. Here, that means multiplying the 1 plus tangent of u numerator by tangent of u over tangent of u plus 1. The common factor 1 plus tangent of u can be cancelled in the numerator and the denominator of the new fraction. And that equals tangent of u, establishing the identity. Here's another example of an identity that we would like to establish. The left-hand side is more complicated than the right-hand side, so let's work on simplifying the left side. We add the two fractions together by rewriting each so that they both have the common denominator 1 plus cosine theta times sine theta. Next, we multiply out the 1 plus cosine theta squared term in the numerator, and we end up with the numerator shown, which contains 4 terms. We group the sine squared theta and cosine squared theta terms together, because we'd like to use the identity sine squared theta plus cosine squared theta is equal to 1. We substitute in the 1, and the numerator becomes 1 plus 1 plus 2 cosine of theta, which simplifies to 2 plus 2 cosine theta. We factor out the 2 in the numerator, and when we do, we see that both the numerator and the denominator contain the factors 1 plus cosine theta. We cancel out these factors, yielding 2 over sine theta, which equals 2 times cosecant theta. And we've shown that the original equation is an identity. Now we would like to show that the equation tangent v plus cotangent v over secant v times cosecant v equals 1. We replace tangent of v with sine v over cosine v, and cotangent v with cosine v over sine v. We rewrite secant v as 1 over cosine v and cosecant v as 1 over sine v. So now the entire left side of the original equation is expressed in terms of sines and cosines. We then add the numerator fractions together, and we multiply the denominator fractions together. And then we see that there's a common factor between the numerator and the denominator, cosine v sine v. We cancel out these terms. We then use the trig identity sine squared theta plus cosine squared theta is equal to 1 and substitute in 1, yielding 1. So now we've shown that the original equation is an identity.